Y in the chat box if I am audible, or type N in the chat box if not audible. Okay, thank you so much. So I hope my screen is visible now. So let me take it to the other device so that there is no disturbance during it. Feel free to type in the chat box if you have any query in between. I will take this all together from my another system. Okay. Okay, so what's the difference simplifier? Look, till now we have gone through the different types of operations which the op-amp can actually perform. For example, the arithmetical operations like addition, filtering, exponentials and logarithmics, and likewise these different operations like differential amplifier, integrator, these things we have done. Now addition, if we are going to do, what about subtraction? If I want to find out the subtraction from any two or multiple values, how I will be doing? So one thing is, we have covered it yesterday, it was somewhat like this. Yeah, this was the summing amplifier. So one thing is, what we can do is, not able to remove this. Anyways, so one thing is, we can take it V1 as positive and V2 as negative. We can take V1 positive and V2 we can take of negative polarity. So instead of V1 plus V2, it will give us V1 plus V2, right? That is one thing. But it is not always possible. When we are going to put some number, so for example, I am writing in the calculator or something, what we used to do, we just put our number, let's say 1, 2, 5, and then we have to put the plus sign or minus sign, let's say 103, and we want the answer. We are not making any number negative itself, because that itself is another operation. So for that purpose, it is not a good choice to have V1 minus V2 in this way. Although our job is done, even if we are using this, that V2 or maybe V1 has been taken negative, then also our job is done. But that's not the way always. So in order to address that issue, let us discuss how the difference amplifier is going to give you V1 minus V2. So here you can see this this I have taken from Texas Instruments. Texas Instruments Private Limited is a big player in VLSI, you might be knowing, and especially it has the market gap in all these things like ADC designing, op-amp designing and related things. It has good market in that. So this is difference amplifier I have taken from the one of the white paper. This is the actually implemented differential amplifier. So if you will be following that document, definitely you can ask your students to perform it, and definitely they will be getting to the actual value, because all the parametric like experimental value with parametric variations they have listed in their document that is available to the public. So if your students are performing this experiment, then it means there is a lot to gain. So that's what I have taken this example. Okay, so now let us understand whatever we discussed yesterday. So we discussed yesterday the inverting mode and non-inverting mode amplifier. So in inverting mode amplifier, we have, this is the negative terminal, this was a feedback resistance, let's say Rx, and this was the input resistance, let's say R1, and this was some input, let's say V1. Positive terminal was connected to the ground. So eventually this terminal becomes virtual ground. Let me take this inverting terminal becomes virtual ground, right? Yeah. So since it is at 0 volt, so this becomes virtual ground. Okay. What will be the output voltage? VO. VO from this we found. How we found this? We applied KVL. What we know, we are presuming that this op-amp is the ideal op-amp. So if it is the ideal op-amp, it means there is no current flowing through this, right? Because the Ri which is seen over here, that is having the infinite value. Ri is equal to infinity. So whatever voltage over here will be having no current flow through this. No current through this, it means IR drop across this is seen, and here you will be having 0. So effectively here you are having 0. Virtual, we call this as, let's say the name of this node is X. So Vx is virtual ground. We will be calling virtual ground. This is very much helpful in many of the applications. Virtual ground means what? Its potential is 0, but it is not physically connected to the ground. And because of that reason, definitely it is going to give us lots of ways in n number of applications, especially when we are talking about ADC and DAC design, in mixed signal IC design circuits, which we have discussed in our previous FTP interfaces in analog and mixed signal IC design. That was discussed. So here, this is 0. Apply the KVL. I told you we can apply KCL or KVL. So here there are only single node is there. If you want to apply KVL, you can apply in this way. That's the way to apply KVL. If you want to apply KCL on X node, you can apply KCL by introducing Vx minus V input divided by R1 is the outgoing current towards input, plus Vx minus Vo upon Rf is the current which is going outside. That's equal to 0. Because Vx is equal to 0, right? Vx is equal to 0. So this way current is going and this way current is going. So when we will make Vx is equal to 0, it's going to give us Vo is equal to minus of Rf upon R1 into Vin. So that's what the inverting amplifier we had the expression for. So it means what? From this particular configuration, what is the effective VO for us? VO, can I say, because of this configuration we are having VO is equal to minus Rf is 20 kilo. Yeah, it is 20 kilo divided by R1 is 10 kilo into Vi1. So that is the component because of Vi1. We are applying at the inverting node. So this becomes 2, minus 2. Vo is equal to minus 2 of Vi1. We have to look into what was the impact of Vi2. So what I told you yesterday, for these type of calculations, first of all we have to make sure all the DC sources are replaced by their internal resistance, right? So what is the internal resistance of this battery? That's ground, right? So if we are going to make it to ground, this is grounded and this is V reference, this is also grounded. So between these two grounds, what can we expect? We can expect that this is also zero potential, right? This is also at zero potential. So it means we are having the component of Vi1 is given by 20 by 10 Vi1 minus 20 by 10 Vi1 at the output. That is because of first one. Now because of V2, how much component we can have at the output, let us consider that. So for considering that, we have to replace this one, this Vi1 with the ground. So this Vi1, we are going to make it to the ground. So this is, yeah, this is the ground. If you want to make it to the ground, so what will be the component of the inverting terminal? That is 0. Now we will be coming to the non-inverting terminal. So for the non-inverting terminal, we are going to make it Vi2. So Vi2 will be putting something, but at the same time, we are having V reference also grounded, because that is also one of the DC source, right? Although that is constant, but that is a DC source. So only this component, Vi2 component, is existing. All other components we will be removing. So let us take only this component, and yeah. So yeah, we have grounded this. It is not there. Because of this, we got this value. Now because of this, how much we can get? So look at this configuration. What we know for non-inverting terminal, whatever we know is, if this is some terminal, let's say A, then whatever VA we have, multiple of that 1 plus RF upon R1 will be appearing at the output. This is what we know. So with this knowledge, let us calculate that how much we will be getting at the output. With the help of this, let us understand this. So let us calculate the for this particular. So we are having our new circuit is configured in this way. This was grounded. This was my R1 RF. Again, this is grounded. This is my Vi2. And this is what my VO2. Because of Vi2, whatever output I will be getting, that is my VO2. So I am applying the superposition from again. So what will be my VO2? I can write, let's say this terminal is A. Non-inverting terminal, I am saying that this is A. And here I was having R2 and R4. This was my R2 and this was my R4. This was R1 and this was R3. Okay, R3 is equal to RF. So now I know that I have to calculate VA. First of all, calculate VA. So I can calculate VA by the voltage division rule. Here I am just highlighting by another color. See, this is the supply. This supply is going from here to here. And this supply doesn't contribute to the current which is entering into this node. Right? It is not contributing to that current. It means this is the only path for this voltage to supply the current. So it means I will be using this. This means Vi2 is supplying the current R2 plus R4, and then multiples of R4 is going to appear at VA. So this is simply the voltage division rule. Means what will be the voltage appearing across R4 can be given by total voltage divided by the sum of resistances into the resistance. That is the voltage division. So this rule says that VA, we are getting this much. Now in terms of VA, since this becomes the non-inverting terminal now, non-inverting amplifier now. So non-inverting amplifier means it's going to give us VO2 . Yes, it is VO2 is equal to 1 plus RF upon R1 into the input at non-inverting terminal, and that is what? That is VA. So with the help of this, what is my output? Because of V2, I am having the output 1 plus RF upon R1 into VA. So VA can be written as R4 upon R2 plus R4 into V2. Let's say VI2. So this much of voltage is contributed because of the input 2, VI2. Now let us find out, there was a third supply also, that was V reference. So we will be considering the third case. In the third case, let me change the color. In the third case, let us consider that this is the only supply which is available, and VI1 and VI2 are not available with us. If that's the case, it means what? It means again it is going to contribute to the non-inverting terminal. So non-inverting terminal I2 is not existing over there, so I am putting ground over here. Okay, again find out the new value of VA, because A is the terminal. Let's say this time it is A, we are having VAR is the value. So what will be the VAR value? VAR, because of the reference supply only, can be written as, look, this supply is contributing towards this way in this particular configuration. So we'll be having V reference upon R2 plus R4, that is the current contribution because of V reference, and into R2, that is the voltage. See, the current is coming V reference upon total resistance through this, into that current into this resistance is the voltage seen over this A terminal. So this becomes VAR. Fine. Now this VAR we have to take into consideration for our VO calculation. So using this, what we can have, because of this VO, let's say VOR, we have V reference. So this will become 1 plus RF upon RF upon R1 into whatever VAR and replacing this VAR with the actual value. And what was this actual value? This actual value was nothing but V reference. It was V reference into R2 upon R2 plus R4. Yes, so this is the VOR value. VO2 value was 1 plus RF upon R1 into VI2 into R4 upon R2 plus R4. And what was, because of input 1, but which was the inverting terminal, so it was minus RF upon R1 into V in 1. Yes, so these were the three values, VOR1, VOR2, VO2 and VOR 1, 2 and R, because of the input 1, input 2 and reference input. What we have to do according to the superposition law, we have to add up all these, right? So if we are going to add up all these, what we will be getting? The final VO can be written as the sum of all these VOs. So because of the inverting input, because of the non-inverting one, and because of the reference supply VR, and we are getting this minus RF upon R1 into V in 1 plus 1 plus RF upon R1 into V into R4 upon R2 plus R4, and this because 1 plus RF upon R1 was common to the reference supply and the input 2. So let us add the other thing over here also. So this becomes V reference into R2 upon R2 plus R4. Now can you see what is the common in this? Look, denominator for both of these is common, right? Denominator R2 plus R4 is common in both of these. So take out the denominator. What you are left with? So taking out the denominator, you are having this component is replaced by 1 plus Rf upon R1 into, divided by R2 plus R4 into V into R4 plus V reference into R2. Yeah, so this is the expression along with this, and this is your final expression. Now in this expression, we are not able to figure out whether we are getting Vin minus V2 or not. So let us find out whether we can have this or not. So let's do some assumptions in this to make it a difference amplifier, a subtractor. So what assumptions we can have? Just have a look at the signs. What signs we have? V in is negatively signed over here. V in is having negative sign. And what about V into? That is with positive sign. But along with that, you can have the V reference also. So I am having the assumption that R1 is equal to R2 is equal to R3 is equal to R4. If that's the case, then in this special case, let's say VO dash is this special case, so it becomes Rf upon R1 becomes 1, so it means it becomes Vin. Plus, look at this is 1 plus Rf upon R1. So this becomes 1 plus Rf upon R1 because both of these are same. Rf was equal to R3, right? So this becomes 1, R2 is 1 and, R2 plus R4 becomes 1 plus 1 into R1, let's say, because both of these are having equal resistance equal to R1. Likewise, from the top also R2, R4 are same equal to R1, so I have taken R1 as common. So now it becomes into V into plus V reference. And if you want to simplify it, so this particular thing is getting cancelled and you are having the final expression. This is getting cancelled away, this 2 is getting cancelled away, and you are having the final expression as V in 2 minus V in 1 plus V reference. So this is what you will be having when you are going to put this special condition that R1, R2, R3, R4, all of these are equal. You can see over here that this is going to give you V in 1, difference of V in 2 minus V in 1, right? It's going to give you the difference between 2 plus V reference. This V reference, we are going to shift it. It's up to us. If we want to give some DC shift, then that can be given as V reference. Okay. Otherwise, this V in 1 minus V in 1 and V in 2 difference will be having that output. And here, if we want to find out the gain, what is the gain? Differential gain can be represented as delta VO over delta VD. VD is the difference between the positive terminal and the negative terminal voltages. So this difference is nothing but V in 2 minus V in 1. So can I say that my gain is equal to 1 in this particular case, right? So the gain becomes 1 in this particular case, and this is how we can create the difference amplifier. Any questions so far in this? Do you have any questions in this? Please type N in the chat box if you don't have any questions. Thank you so much. Okay, so let us proceed now. So I told you that I have taken this design from Texas Instruments. So if you want to give this as an experiment, okay, first let us take to the actual values which are listed in this experimental setup. So in this experimental setup, the actual values are given. Actually, R4 is twice of R2 and R3 is also twice of R1. So taking these things into consideration, what we can have, taking these things into consideration, if I am going to find out what I will be having at the output, we can represent it in this way. So if we can recall what we have created, because of this, I was having VO is equal to minus RF upon R1. So minus RF is this 20K upon 10K into VI1 plus, because of this only, what you had 1 plus RF upon R1, that is nothing but 2, right? Because this 0 is getting cancelled away, RF upon R1 becomes 2. So I am replacing it by that particular value. Let's have that value. So 1 plus 2. Okay. Next, V into R2 divided by R2 plus R4. That is 10 plus R2 is 10 kilo. This is 10 kilo. Plus 10 plus 20 kilo. R2 plus R4. And the same thing towards this way, plus V reference into R2. Yeah, it was R4 20. Let me correct it. So this one was 20 kilo and this is R2. This is 10 kilo. So this kilo we will be taking common, these zeros will be taking common and that will get cancelled out. Look at this, this is 3 and this becomes 30K. So K is getting cancelled away from here and here, and you are left with this 3 is getting cancelled away from this and this. Zeros are getting cancelled away because this 0 taking outside becomes 30 over here and downside it is already 30. It will make, if I am taking 10 common from 10K common from this becomes 30K and this is already 30K. So we are left with VO is equal to minus of VI1 plus twice of V into plus V reference. So for this particular case, we are having this much of our output voltage, right? We will be having this as our output voltage. So for this type of circuits, how these circuits are designed? First of all, I told you yesterday that this op-amp is prepared by the different MOSFET circuits or BJT circuits, which are taken as at the input. These are taken as the difference amplifier, and after that, what is the difference amplifier? Let us take it. So it can be represented in this way. Difference amplifier means symmetric devices will be taken up and the output will be taken from all the opposite branches. It is clear from this one, right? So here you can see there are two stages and both of these stages are symmetric to each other, and then the output is taken from the different branches. It may be from one branch or different branch. This is actually the input, inverting and non-inverting input. Then corresponding will be giving this input to the next stage to amplify from there we'll be having the output to give to the next stage, which is the level shifting stage, and then finally the output stage, so that it can produce the low amplification. So here you can see everywhere the BJT is there. This BJT can be replaced with the help of MOSFET. So what type of experiment you can give to your students? You can give to your students, okay, design the difference amplifier with so and so configuration. So to design that, there are n number of things we need to take care of. For example, what should be CMRR, common mode rejection ratio, what should be PSRR, power supply rejection ratio, what should be the offset voltage, and all these things we have to take into consideration. We are saying that ideally the AV, the gain is infinity, but actually that is no, right? We are saying that the input impedance is ideally infinity, but that is not actually. Output impedance we are saying 0, but it is not actually. So we will be giving some actual parameters, and those actual parameters will ask the students to design such an open circuit. So designing the open circuit with a good performance parameters is really very difficult. This type of projects can be given to the students, and in order to give such type of projects to the students, you may utilize cadence virtuoso that gives you the actual flavor of the design. Cadence virtuoso is a commercial software. You can design your circuits. We have discussed the LT Spice. We have discussed the open source virtual labs, and LT Spice is also open source. So if we are using Cadence Virtuoso, you can go up to your GDS creation, netlist generation, till layout. You can go, and you can give that file file to your any fabrication lab, and your actual hardware will get designed. So that's the difference between the open source softwares and the commercial softwares. So if your students are really willing to design something good, ask them to work on Cadence Virtuoso. If it might be possible that many of the colleges, or maybe your college is not having this software, what you can do is you can contact to some lab in across the country. There are more than hundreds of the institutions. Those are having this particular software. You can get connected with those faculty members, and your student can go there, can access the lab, and in this way you can have your good design. These type of designs can be published because you are doing some real work, and that is contributing to the research community. So that is the way how we can go towards the research for this. So let us come back to the topic. Yeah, so we have discussed the difference amplifier. In the difference amplifier, we have discussed the actual cases, whatever were given over here, and how we are getting VO is equal to V2 plus V2 minus V1 plus V reference. V reference is the biasing properties. Let's say you are going to give your V in and V in 1 and V in 2 as a sinusoidal signal. You have to make sure that your sinusoidal signals are good enough so that your op-amp is operating in the linear mode of operation. In the morning's lecture, you were told that if somehow your output gain is in such a way that it is crossing the limits are set by so the limits are set by the plus minus power supply, VCC and VE. These are the power supplies. So this VCC and VE came into picture because earlier the first design of op-amp was created with the help of BJT. So in BJT there are three terminals. One is the collector, emitter and base. So these three terminals, these supplies were connected to, most of the supplies are connected to the collector or emitter. Emitter is negative supply, because we are, for example, most commonly used is NPN transistor. So for NPN transistor, we are expected to keep our emitter at low and collector at high, because this becomes, let's say, NPN. So for a simple mode of operation, active region, what we used to have is your first junction, this base emitter junction must be in forward bias. So if it is in forward bias, it means what? Your emitter is expected to be at lower potential, right? And this BC junction is expected to be in reverse bias. So if it is in reverse bias, it means you are expected this end has to be connected in with positive supply. So that's what we have positive supply as VCC and negative supply as VEE. Understood this? You may type Y in the chat box if understood so that I can proceed. Yeah, shall I proceed? Am I audible? Dr. Geeta, am I audible? Am I audible? Hello? 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 Okay. So, how this type of amplifiers can be designed? You can design it in this way. The steps are given. How you will be designing this? Use the op-amp in the linear operating mode. Linear operating mode means you are not going beyond the supplies. Let's say, for example, in this particular case, let us see that you are having VO because of the input 1 is equal to minus RF upon R1 into V in 1. Let's say V in 1 you have given the sinusoidal input. So this sinusoidal input is in this way, which is having its peak to peak value. We will be starting from 1 volt, let's say 10 volt to minus 10 volt to plus 10 volt. Now let's say your RF is going twice of R1. So RF1, R1 is twice. So it means what should be your output? Your output according to this, it should go from minus 20 peak to peak to plus 20 peak to peak, plus 20 volt. But what we know that the output will not be able to extend beyond the supply. So it means you are not getting the complete waveform. So you will be getting some such type of waveform, which is limited to minus 15 volt, the standard for op-amp 741, minus 15 volt to plus 15. So this is not the linear mode of operation, right? Linear mode of operation, you will be having the linear function. The output and inputs are the linear functions of each other, right? So in this case, these are not linear functions of each other. So first of all, you have to make sure that for amplifier design, you have to make sure that the linear mode of operation you will be having. For example, when you are doing some design in the cadence, and let's say you want to prepare some amplifier. So what is the mode of operation you would like to choose? I am going to give you the three options. For amplifier, you can choose cutoff mode. So you can choose cutoff mode. You can choose active mode, or you can choose saturation mode of operation. So which one you would like to select out of these? I want to design an amplifier in cadence. Which one? Or in simple, in any tool you want to design, on paper let's say you want to design. So you will ensure that the transistor is working in which mode of operation. So of course the active mode of operation I would be working. I have to make sure, first of all, with all the biasing conditions, I will be applying KCL, KVL wherever is applicable, and I will make sure that my forward bias is there in the EB junction, emitter base junction, and that is the forward bias, and the base collector junction actually is reverse bias. This is the forward bias and that's the reverse bias. And if it is MOSFET, then I will make it ensure that my current E is given by this formula, I is equal to mu n squared W by L VGS minus VTH square, right, into 1 plus lambda VDS. So how I'll be getting that? I'll make sure that my input is greater than VTH, and at the same time VDS is also greater than my VGS minus VTH. That I'll make sure. And if you are going to make it sure in this way, it means after that you can proceed further. So first of all, the first design step is you are going to make sure that your device is working in your system, your op-amp is going to work in the linear operating region. Okay, so that the inputs are not exceeding. Then you have to decide that the input impedance is determined by the input resistive network, and make sure these values are large when compared to the output impedance of the source. So although the input impedance cannot be infinity, we know, but the ratio of the output impedance to the input impedance should be very large, so that we can make it very large means towards the infinity we can make it. Okay. Next one is we have to use high value resistors that can degrade the phase margin of the circuit, and that can also introduce the additional noise in the circuit. So we have to avoid the high value resistors, so that the additional noise is not being introduced. Next one is we have to avoid placing the capacitive loads directly on the output of the amplifier to minimize the stability issues. So what are the stability issues? Your system is not going to give the stable output for that particular range. So that is the stability issue. In order to avoid that, you will make sure that the capacitive load is not directly put at the output. Yeah. So next one is the small signal bandwidth. This is being determined by the noise margin or the non-inverting gain. Op-amp gain bandwidth product, that is very important parameter. GBP gain bandwidth product. Additional filtering can be accomplished by adding a capacitor in parallel to R3 and R4. Adding capacitors in parallel to this will also improve the stability of the circuit if high value resistors are used. So this you need to take into consideration while designing. Large signal performance may be limited by the slew rate. Slew rate is what? dB out over dk. So this is also one of the performance parameter. So you have to control this also. This is expected to be as high as possible. So the large signal performance may be limited by the slew rate. Therefore, check the maximum output swing versus the frequency plot in the datasheet to minimize the slew induced distortion. Means if quickly your output is being changed, then many a times it is seen that your output is distorted. So in order to avoid that type of distortion, you have to make sure that your output is working fine in all these ranges. That you have to take a design note. For yeah, so for more information regarding to this, you can refer their document, their white paper, which is publicly available. And yeah, these are the design notes. While designing any open, you have to take difference amplifier, you have to take into consideration, and then you have to proceed. So if you have any questions so far, please feel free to ask so that we can proceed to the next topic. Type N in the chat box if you don't have any questions so far. You may type N in the chat box if you don't have any questions so far. Thank you. Yeah. So whatever calculations we have completed, that can be given with the help of this. This is the derivation I have already taken up, and this is the final expression. If we are going to make R1 equal to R4, we'll be having the VO is equal to VI2 minus VI1 into R3 upon R1. So what will be the differential gain in this case? The differential gain can be written as dVO upon dV common or V difference, and that is nothing but R3 upon R1. So you can see the gain can be amplified, the difference gain can be amplified. So it can also, this difference amplifier can work like your V in 2 minus V in 1, that is one of the application. Another of the application is it can work like the difference amplifier with the help of putting the suitable resistances. Like in this particular case, we will make it symmetric by making it R1 equal to R2 and R3 equal to R4. So it will become the difference amplifier, which is going to amplify the difference, and the difference gain will be R3 by R1, right? So if this R3 by R1 in this particular case is twice, so the gain will be, the difference gain will be twice in this particular case, right? Shall I proceed now? Yeah. So in the previous expression, I have made one mistake, I believe. When I made this, for this, when I made it, it was good. So it was 2, yes, it is 2, and the other 2 came with plus 2V in 2 and plus V reference we found. So we are having the difference amplified gain in this way. Now let us take another example so that you can understand how it can be taken up, these type of circuits, how these can be useful to the electrical engineer. So instrumentation amplifier is one of the very famous amplifier, you might have heard about it. It actually reduces the voice, it actually reduces the noise. Op-amp itself reduces the noise, but instrumentation amplifier on the top of whatever op-amp produces, apart from that it is going to reduce it. So instrumentation amplifier is actually one which we are looking for noise rejection, especially the common mode noise rejection. So in this particular, this is the simple configuration for instrumentation amplifier. In this, we have two things. There are two blocks. The first block is the input buffer amplifier state, and the second block is the output difference amplifier. So the output difference amplifier in this particular case, R1, R2, R3, R4, all of these are equal. So if all of these are equal, it means whatever Vi1 you are getting, let's say this is V1 and this is V2. So the output of this can be given as V2 minus V1, because V reference is grounded, right? If you have some value of a V reference, then that will get added over here. Now you have to find out V1 and V2. So in order to find out V1 and V2, you'll just take into consideration this one and this one. So here what you can look into, look at this, the common mode input is going to the input of this, to the positive terminal and the positive terminal of this. Okay. So if I want to find out what is the input over here, so just apply KVL from this to this, and you will feel that the input over the positive edge of U2. What is the positive edge of U2? Applying the KVL, I will get that this is equal to Vi. So this is Vi1 plus Vsim, VSCM. That is the common mode. Vi1 plus V common mode. Yes. And likewise, if we look at the bottom one U3, then the voltage appearing over here is equal to VCM. That is nothing but the DC supply. And then this is Vi2. See, whenever we are going to create some amplifiers, so the amplifiers are used for AC or DC. Please type in the chat box whether the amplifiers are used for AC or DC. Right, AC, if it is amplification is used for AC, or if it is used for DC, please write DC. I hope you can hear me, and I expect the answer from you. It can be wrong, either it can be right or wrong. If it is right, it means it is good. If it is wrong, you will be able to correct it. So basically, the AC is what we will be using for amplification, right? DC is the constant, right? It's a straight line. You cannot amplify that. So if you want to amplify something, you have to apply AC signal. So here you can see the common mode is actually a DC level, and these are actually the AC signals. So these AC signals are going to override. These AC signals are going to override, and then you will be having these signals Vi1 plus Vcm and Vi2 plus Vcm at U3 positive terminal. Now what I know about these two, both of these are actually non-inverting terminal amplifiers. So for non-inverting terminal amplifiers, what I know is that my VO is equal to 1 plus Rf upon R1 into V1, whatever at, or let's say V plus, whatever at the positive terminal of the op amp I have supplied the voltage 1 plus Rf upon R1. So what is Rf? Whatever the negative feedback supplied, that is your Rf. What is R1? From here to the ground. Whatever you have supplied from here to the ground, that is your Rf. Okay, so in this particular case, look at this, that there is a symmetry between two. Yeah, this is symmetric and this is also symmetric. Both of these are actually at the same potential, same DC level. So whatever DC level they are having over here, virtually that DC level is going to appear over here and here. So keeping that thing in mind, we can figure out that actually this will be having somewhere in the middle of it, it will be having its ground. It will be having its ground somewhere in it, right? And using that you can find out its total gain. So in this way, the instrumentation amplifier can be solved, and it can be taken as a project by the students, maybe use your PG students, and yes, it is a good learning for them. So if you have any questions so far, you may ask. Otherwise, let us proceed for a 10 to 15 minutes practical session regarding this op amp amplifier. Type in the chat box if you have any question. If you don't have, you may type N in the chat box. Okay, thank you so much. Fine. So before this, let me take one more circuit. Let me introduce you. Just now you were introduced by a logarithmic amplifier. So let's take it in this way. This is your virtual ground, and this is, let's say, your diode is connected in this way, and this is your output VO. Okay, so instead of this, let me connect the diode this place. Let's say there is a resistance RF, its value, and there is a diode over here, and here you are having some V in voltage. So this V in voltage cannot be controlled arbitrarily, right? We know that the forward bias voltage of the diode cannot exceed zero point 0.7. So either you apply some resistance in series with this. But for the sake of simplicity, I am not going to apply that particular resistance so that I can show you how it will go, how it will be working. So this V in is directly, I can say that look, this positive is grounded. So can I say that I will be having zero potential over here? The reason being the drop across this is zero, and this are connected to a very high resistance. That we can consider if there is no drop, it means that is just like a wire. So it means I'll be having zero potential over here. Now the potential over here is zero, and here this is the P positive terminal of the diode is connected to V in. So what will be the current? According to the diode current equation, we can have the reverse saturation current of the diode into exponent of Vd, that is nothing but V in upon Vt minus 1. Okay, so yeah, instead of Vd, let me take V in. Yes, it is V in. So now this current, this much of current is going through this, and after this the same amount of current is going to enter into this, because it is not having any path to enter inside the open. It cannot go inside the open. There is no path. So whatever current is coming from here, the same amount of current is going through this. So what will be my output then? Output can be written as whatever your ID current is into R. So with the help of this, I can represent it in this way: IS into RF into exponent of V in upon Vt. So here you can see that this is how in the operations you need the exponent calculator. So the exponent of anything can be calculated with the help of this formula. So input, you are going to give some input value and you want to find out its exponent of this. So you will be able to find out this value. Now look, if this is going to increase, this is negligibly small, so it can be neglected. This particular component can be neglected, and directly it is going to appear just like the exponent. It is going to appear just like the exponent of it. Now let me take the reverse direction of it. If I am going to actually interchange the RF and this value, then what is going to happen? Let us consider the direction, positions of both of these are reversed. So this is my resistance and I have taken it here. Now what I know, the current through this is V in upon, let's say this is R. V in upon R is the current. Now whatever the diode current whatever current will be seen, that is going through the diode. So what I will be having through the diode, what I can have. So this equation, this green color equation was from the previous one. Now I am going to change the color so that you can understand that what is going to happen by replacing the positions of diode and the resistance. So look at this, the positive terminal you have the VO, V out, and here you have the ground. So what is the diode voltage over here? In this particular case, minus VO is your diode voltage, right? Minus VO is your diode voltage. If this is your diode voltage, yeah, in the previous case, of course, you have the minus sign because the current was entering through this, so this was expected to be the higher potential. So of course the minus sign was there. Sorry, I forgot at that time. Yes, so this is minus VO across the diode. So I can have my diode current is ID is equal to IS into exponent of minus VO upon Vt minus 1. And of course, this is equal to what? V in upon R. Now if put on both of the sides, but I can have, taking log on both of the sides, I can have, see, this is exponent of minus VO upon Vt minus 1. Because the current was good enough, it means we can remove this 1. Okay, so we are left with V in upon Is into R. Yes, I have taken Is from here to here. Now if you are taking the natural log, you are getting VO is equal to Vt, right? Minus of course this minus sign is all together. So Vt and log, natural log of V in upon Is into R. So this Is into R is actually the DC level, right? So you can represent it in this way, that VO is equal to minus Vt let me remove some of the portion. I have not introduced a blank slide just after it. So what I can represent, my VO can be represented in this way, that VO is equal to minus Vt into log of V in and plus some constant. Why constant? Because Vt into log of Is upon Is into R, that is a constant value. This is constant value. So can I say that in this way I can find out my log of whatever input was. So I'll be getting the input in the log form at the output I can have. So here we have covered both of these, like how I can get the exponent, and by changing the position of it I can get the log of it. Okay, so yes, this we have covered. So if you have any questions so far, please feel free to ask. Otherwise, let us take virtual labs for op-amp, which we have not covered. So first of all, you may open this link. I am typing this link in the chat box. You may click on this so that you can follow me. Whatever I will be doing, you will be able to do that along with me. When you will be opening this link, it is the same link which I have shared earlier with the for doing different IV characteristics of diode, Zener diode, etc., etc. So this is the open to draw the circuit. Here the same thing, the instructions are given over here. You have to connect L1, L3, L4, L7, L4, L5, L5, L7, 6, 9, 8, 12, like that you have to connect. Then you have to check on the connections. After checking the connections, so just click on all these things, whatever it's been given. I will check the connections first because we do not have much of the time. So yeah, connections are right. It is telling set resistance R1 and the feedback resistance. So if you look at this is actually checking the connection was correct. So now I am going to set, yes, let me take some good value so that we can visualize it. 10, I have taken it 10 kilo ohms, and let us take the RF value. Let me take it 40. It's 41. Yes, it is 40 now. So it's done. It's and then there is input voltage. So this input voltage, let me take it in this way. So what are the instructions? Click on the check connections. If connected wrong, double click and then set again. Set the resistances, set the feedback resistance, set input from this to this range, and then you have to keep on adding this to the table so that we can have it. So add to the table, then again increase this a little bit, add to the table. Again input is increased, add to the table. Again input is increased, add to the table. So the input we are going to give at the inverting terminal. So the inverting terminal formula becomes RF upon R1. So RF upon R1 becomes 4 over here. So it means 4 times of whatever I will be supplying the input, 4 times of that I should get at the output. Add to the table. Again, okay. So arbitrarily I have taken some values for the input, and now let us plot it. Just like your IV characteristics of your diode, your Zener diode, etc. etc. Okay, so let's plot it. So you can see you'll be having the input in this way and output is in this way. So what was the formula between input and output? Input was given by, let me introduce one more slide. So the input was VO is equal to minus, it is inverting mode, right? So VO is equal to this much. Now VO versus Vin, if I want to find out, can I say that this is the equation of line which is having more than 45 degrees slope minus more than 50. See, tan inverse 4 we have to take, and this is actually negative sign. So for negative sign tan theta means we have to take the slope negative. Tan minus theta is equal to minus tan theta, right? So that's what we will be getting somewhat like this. And this is what we are getting in the characteristics. If we are going to increase over negative direction, it will keep on increasing. It will keep on increasing. It will keep on increasing, but in negative axis, and that's what we are getting. We are confirming the same thing from this. Yeah, output characteristics. Yeah, so these are the output characteristics, and we are getting this thing output and input. Output versus input. We are getting this way. You can see that there is a negative slope, and this is the equation of line. So if this equation of line agrees that your amplifier is going to work in a good manner, because if the linearity is not followed in the amplifier, then there are second order effects, and those second order effects will disturb the amplification. So that's the thing. So another one is the non-inverting. Let us draw for the non-inverting also. So first of all, draw the circuit in this manner, and then this is the resistance, and then this, I will not check, let me check the connections if these are correct. Yeah, connections are right. So let us set this RF and some value of R. Let me take it just double of it. 17 into 2 is 34, right? Yeah, 34. Now let us keep on changing the input. So the input initially is minus 15, add to the table, change it now and keep on adding to the table. So this also, it is going to give us 1 plus Rf upon R1. 1 plus Rf upon R1 is actually in phase. So if you are going to increase the input, it means the output is also going to increase, and it will be tan theta is positive. So it will be in the first quadrant only, or it can come from third quadrant towards the first quadrant only. And let us plot it. So if we are going to plot, you can see that the zero crossover is here. At 0 you are having 0. So left hand side of this way it is third quadrant, and this way it is first quadrant. Yes. So if you have any questions so far, feel free to ask. Otherwise, we'll meet at 11 a.m. tomorrow, and tomorrow's session will be really good, because I'm going to discuss about, that will be especially for the higher end side, that how the different from MOSFET to the advanced devices, how we can proceed. So I will be having a lecture on that tomorrow, and day after tomorrow I will also have one more lecture that will be specific some device and its application to something. And in ending session tomorrow, we'll be having four continuous hour session from C.D. Pilani scientists. So please do not forget to attend these sessions tomorrow. Thank you so much. And let us close for the day. If you have any questions, feel free to ask in the chat box. Please type in the chat box if you have any question. Otherwise, you may type N in the chat box if you don't have any question.